One of the biggest misconceptions about model-based systems engineering is that it's just a modeling activity. Many engineers and managers assume that model-based systems engineering is about drawing diagrams or using a new software tool. It's not. Model-based systems engineering is a lifecycle approach, a way to manage complex systems from start to finish. And if you don't understand the lifecycle, model-based systems engineering can feel confusing, overwhelming, or unnecessary. In this video, we'll take a step-by-step journey through the model-based systems engineering lifecycle. I'll explain what each phase is, what it actually accomplishes, and why it matters, without tools, jargon, or hype. By the end of this video, you'll understand how model-based systems engineering organizes system knowledge, reduces risk, and creates lasting value. Every model-based systems engineering effort begins with requirements, but not in the way most people expect. In traditional systems engineering, requirements are often just text documents. They are written, reviewed, and then stored on a shelf. The problem is that systems evolve, assumptions change, and those documents quickly become outdated. Model-based systems engineering changes this. Requirements in model-based systems engineering are living elements. They define the system intent, guide decisions, and connect directly to architecture and design. The goal in this phase is to clearly understand intent, reduce ambiguity, capture assumptions explicitly, and define system boundaries. For example, consider designing a medical device. If the requirement simply says, "The system shall measure temperature," that statement is ambiguous. Model-based systems engineering captures the context, conditions, and constraints, making it clear how that requirement will be implemented, tested, and verified. If requirements aren't clear, everything that follows becomes guesswork, and complexity multiplies. Capturing requirements properly sets the foundation for the entire model-based systems engineering process. This is where the system's DNA is defined, before any architecture, design, or simulation begins. Taking the time to do this carefully pays off in the later phases, preventing errors, rework, and miscommunication. Once requirements are well defined, we move to system architecture. Architecture is the blueprint for the system. It breaks the system into major elements, defines responsibilities, and identifies interfaces between components. It's not just about drawing diagrams. Architecture is about managing complexity intentionally. Without a good architecture, complexity hides itself and causes surprises later. Good architecture allows teams to see how subsystems interact, where potential conflicts may arise, and how changes will ripple through the system. For example, in aerospace systems, there are dozens of subsystems: propulsion, avionics, sensors, and controls. A well-defined architecture ensures these subsystems integrate correctly and safely. Poor architecture, on the other hand, hides problems until integration testing, often leading to costly delays and fixes. Architecture is the backbone that supports the rest of the model-based systems engineering lifecycle. It ensures that complexity is managed, not multiplied, and that the system can evolve without chaos. This is where model-based systems engineering really begins to show its power. Analysis and simulation allow engineers to explore design trade-offs, understand system behavior, identify risks, and evaluate what-if scenarios, all before building physical prototypes. You don't simulate everything, just what matters most to system success. For example, in a large software-hardware system, you might simulate communication delays, response times, or interface behavior. These simulations reveal potential problems early, allowing teams to adjust the design before costly errors occur. Model-based systems engineering shifts learning from late-stage testing to early analysis. Instead of discovering issues after production, teams can identify and solve them in the model. This not only saves time and cost, but it also increases confidence in the system design. Analysis in this phase directly informs architecture decisions. It creates a feedback loop that continuously improves understanding of the system. Verification and validation are often misunderstood in engineering projects. Verification asks the question, did we build it right? Validation asks, did we build the right thing? In model-based systems engineering, verification is tied to requirements and occurs continuously throughout the lifecycle, rather than being left until the end. Validation is integrated as well, ensuring that the system meets real-world needs at every stage. Models allow engineers to continuously check requirements, trace changes, and ensure that the system performs as intended. This continuous approach dramatically reduces late-stage surprises, rework, and cost overruns. Instead of discovering a major flaw during final testing, model-based systems engineering allows teams to detect and correct it early in the lifecycle. Verification and validation are no longer separate, disconnected steps. They are embedded within every phase of model-based systems engineering. The final phase, deployment and reuse, is often overlooked, yet it is where model-based systems engineering delivers long-term value. Once the system is delivered, the models remain as a living representation of the system. They preserve knowledge, support future upgrades, and enable reuse across other projects. Imagine a team building a similar system years later. With model-based systems engineering models, they can quickly understand prior design decisions, avoid repeating mistakes, and adapt components efficiently. This reduces knowledge loss and increases efficiency across programs. The true value of model-based systems engineering emerges after the first system is delivered. It transforms model-based systems engineering from a single project tool into a strategic advantage for organizations. Deployment and reuse create lasting benefits, saving time, reducing risk, and improving system quality for future initiatives. The model-based systems engineering lifecycle is the backbone of complex system development. When teams understand how each phase connects and why it matters, model-based systems engineering becomes far more approachable. If you want a guided, beginner-friendly introduction, we offer a free Model-Based Systems Engineering Foundations module that walks through these concepts step by step. Check the link below, and in the next video, we'll explore the systems modeling language and the diagrams that actually matter. Follow for model-based systems engineering without the complexity.